Welcome. Let's look at applications of using the slope-intercept form or graphing equations with it. So let's analyze what's happening here. Okay, this is a rental company charges $8 per hour, and renters must also pay $5 for a helmet. We're going to write an equation. We're going to graph the equation. Okay, so I guess I actually ought to say just write. We're going to write the equation. We're going to graph it. And then we're going to answer it, the cost when there's 7 hours, and if they pay 92, how long, $92, how long were they renting the bike? So we are told here to use C for cost and H for hours. So that means what we have here is an H for that. And then the total cost is a C. So right now, I want to analyze what's happening here. And I can see for 1 hour, I would pay $8. Plus, I'm going to pay the $5 helmet fee for the helmet. And for 2 hours, it's going to be $8 times 2 plus the $5 helmet fee. For 3 hours, it's going to be $8 times 3 plus 5. I don't really need this anymore. So if I did 4 hours, that means it's 8 times 4 plus 5. So I don't know how many hours I'm going to have it. We'll call them X, which means it's 8X plus 5. Ah, now that helps. So what we have is that the total cost is going to be equal to 8, or actually, let's see. C, the cost, is going to be equal to 8X plus 5. That's the equation. That's 1 here. I should have done an ABC, but we'll do 1. And then 2 is to graph it. So now what I see is like, what do I do here? Well, we're going to go up to $92, I guess, and plus it's going to be quite a few dollars. And then the hours, time is always the x-axis when you're graphing things, which means that this would be the number of hours, or actually, wouldn't it be the total cost? I think it would be, because hours is time. So we'll put cost here and time here. And the cost is in dollars. So that means I won't have to write them up. And let's go by tens, 20, 30, because think about the problem for a moment. You'll see it makes more sense to go by tens than by any other number. And the time, well, we're going 8, 10 hours. Most people would not have the mountain bikes for longer than that. 2, 3, 4, 5, 6, 7, 8, 9, and 10. And we'll say that it is in terms of hours. It's not like minutes or days. It's going to be hours. Days could be appropriate for long-term rentals, but they have to be charged a lot of money. All right, well, now let's graph a few things. Well, how do we graph it? Well, we could make a table, but we can also use this equation because this gives us a y-intercept of 5. Let's get all that back there. Okay, well, back again. All right, good enough. Oh, I don't like having that. It needs to be filled in. So we have a y-intercept of 5. I'll use nice red for it. Right down here of 5. And we have a slope of 8. Okay, so m is equal to 8 over 1. I can do that, or I can plot. I'm thinking I can't do 8s easily there. So let's put in a couple of numbers. Let's do instead a table, an XY table. And let's put something like 5. We already have halfway this one here. So if I put 5, that's going to be 8 times 5 plus 5. That's $45. So at 5, I go to where 45 would be. And then let's put in the 10 because that's an easy number to work with. That's 85. So for 10, I'll go to 80 and halfway through. And now I'll do an equation. I just put an arrow. Uh-oh, if I put an arrow this way, that is nonsensical, meaning it doesn't make sense. I can't go into negative hours. So that means this would be an inappropriate place to put an arrow on the left side. Only an arrow on the right side is needed. Well, now I've graphed it, which means 2 is done. So I've done 1, and I've done 2. Now let's figure out the cost for someone who rents the bike for 7 hours. I'll call this 3 here. Okay. So we're going to take that equation. The cost is 8x plus 5. And for 7 hours, the cost is 8 times 7 plus 5. So 8 times 7 is 56, 63, 56 plus 5. Okay. And that means the cost is 61, or we'll say $61. So this line is the graph. That's 2, and then this is 3. Then there's the fourth thing to do. Okay, so the fourth thing to do is if someone pays $92, that means the cost here is 92 equals 8x plus 5. We have to solve for the x. So I'm going to subtract 5 from both sides. And we get 80, see, 5 from 12, that's 88. No, 87. 87 equals 8x. Now here, when we divide, now this is an interesting one, and I think I would have used some of this space down here, but I'm going to move it up over to here. So I'm going to have 87 equals 8x. And when I divide by the 8, I get that x is 10 point something. Okay, this is an interesting amount now. Okay. It's going to be just under, probably like about 10.9. Well, here's the thing. That means almost 11 hours. And you know, when you're charged for a bike, if you do like 10 and a half or 10 and 3/4 hours, you don't get any money back. It's usually the full hour. You start an hour, you pay for the full hour. So 11 would be the most amount of time. So they rented it for 11 hours and they used it for just under that 11. So I'm going to put 11 hours. And that's for part 4. So that's with making an equation, graphing it, and then answering a couple equations based on that graph or the equation. Let's take a look at one more here. Okay, now this is an interesting kind of problem. And it's going to use the same ideas, but it's going to be a little more complicated type of thing. So let's take a look at it. We don't, okay, magazine begins with a circulation of 500,000. Increases by that much, 33,000 and some each year. We'll write an equation, C after T years. So we'll use the C and we'll use a T. Okay? And so we need to write an equation, and we're going to graph the equation, and then we're going to answer 2 questions. Okay? After 56 years, or in what year will we reach 3 million? All right, so let's think about how we're going to make the equation. So for this, what I will do is think about what happens each year. So in the first year, year 1, we have 500,000 to start. Well, what I'm going to do, I'll do 500,000 plus an increase of 33,388. In year 2, we have the 500,000 plus, well, now it's 2 of these, so it's 33,388 times 2. And that means the first one was 1. So if I do the third one, it'll be the same thing, but with a 3 there. So that means what I do, if it's X number of years, it's 500,000 plus 33,388X. Well, this looks suspiciously like a slope in y-intercept, and that means we need to write it in terms of the other way around. So what I would say is total, C was circulation here, not cost. I think I said cost before, but circulation meaning how many papers are being, or how many magazines are being sent out. So the total circulation is equal to 33,388 times, now not X, remember this was T years. So instead of X, we need to use it as a T. And that makes sense for T. Y would have been better for the number of years, except Y has a different meaning for it. Plus the original 500,000. So that's an equation. And that, no matter how many years you put in, you can now figure out what the increase is to add to the original amount. That is number one. Let's get back here. Okay. And that's one. Now, what does the slope represent here? What's the slope represent and the c-intercept? So it's not y-intercept now, it's sleep-intercept. This is the increase by year. And this, the y-intercept, is the original. Let's write that so it's more easily read. Original starting amount. Okay, now let's graph it. We're going to graph it. We'll figure out what numbers to put in here. Right, so we're going to know that this is time. I'll graph it and starting with black. The time, and that's in years. And this one's the circulation. Now, we can go up 500,000 to start, and we could go up to millions in it. But with that lower increase, we're not going to get to millions. So let's make 500,000 like the middle. And so the circulation in thousands. That means I can put 500 in the middle, and then 1,000 here, which would be 1 million. And that would be 600,000, 700,000, 800,000, 900,000, and so on down. 200,000, 300,000, 400,000. Okay, now it looks, at least I've got all the numbers right on it. And then the number of years, after 56 years, well, we don't have to go that many. We can just do the first few on here. Okay, so, or I can go by like 5s or 10s. So let's do it by 5s. So 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. So it might end up with a lot here. I may go off the graph. Maybe I should have gone past 1 million there. I don't know. So let's actually now plot a few and see. Well, actually, the y-intercept we know here. The y-intercept is at 500,000. And let's put in a few other numbers. Let's try, say, 20, okay, and see what happens. So part 2, okay, I'm going to do that the circulation is equal to 33,388 times 388 times, say, well, actually, let's do the 10 first, see which way it goes, because that's easier as a number. Okay, plus the 500,000. So I'm going to put a 0 after this. 3 instead of 33,000, 333,880 plus the 500 million or 500,000 gives me 833,880. So at 10, we're at 800 and a little bit more. And what I see now is it looks like I'm probably going to go off it. Let's put 20. D is equal to, blue, 33,388, 20 plus the 500,000. Well, that means doubling that. That's going to be 6, 6, 7 up, I think, for that. I'll use a calculator and then have this one already set, so we'll do it now. 388 times 20, 667,760 plus the 500,000 gives me 11,67760 So that's 1.1 million. So I'm going to go actually up a little bit here. That would be 1100. This would be 1200. So I'm going to go at 20. I'm going to go up to past it, a little off the graph here. Okay, let's make that one actually more in the middle, really. Was it? Oh, it's a little bit more than the middle. It's supposed to be 833. No, this is about a third there. And then that one I'll estimate about there. That actually looks like that they're pretty close to in line. Not perfectly, but given this imperfect drawing, then that would be enough there. I can't put an arrow going that way, going down, because that was a starting point. There was definitely nothing before that. Okay, so the arrow, so it's going approximately like that. In fact, now that I see it, I want to move that over a little. Okay. So, whoops. Didn't mean for you to move. Hold on just a second so I can make this a little more precise. Not completely precise because I can't get that last dot in what probably is the best place for it. So that's about what it would look like if I started with 500 and went to 1 million and went by every 50 million or went up to 2 million. Then maybe this would be the arrow would look a little different, but still working with these numbers and these numbers, this one works pretty well. Okay, let's do 3. So what I just did here is write an equation, graph it. Let's see after 56 years what would happen. And that's taking the equation and putting 56 in for the time. So for 3, C is equal to 3, 3, 8, 8. So too many 3s. 33,388. Okay, times 56 plus 500,000. Okay, so what that's going to give us is, and I will double check my own answer with it, times 56. That's, oh boy, 1,800,000, almost 1,900,000, plus the 500,000. Okay, gives us, the circulation is 236, oh no, 2,369,728 magazines. That's a lot of them. That's come up way a lot. That's if the trend actually continued. It could be that they slowed down during some years or sped up during, or had more of them during some years. So now, if it began in 44 and the trend continues, in what year would it reach the 3 million? So what we're going to do here, we can see from the other number, it's going to be past 56 years. So what we'll do here is set this up where we're going to say the fourth one. Okay, we now know that the circulation amount is 3 billion. Okay, let's get enough zeros there to cover that. 3 million is equal to 3,338x plus the 500,000. I don't like that. I need more space. So I'm going to actually do it now. More space here. Okay. So for part 4, this is going to be 3 million equals 3,388 x plus 5s. And we want to isolate the x. We want to find how many years to get to that number, the 3 million. At this point, we just simply solve it like we would any kind of problem. So I'm going to subtract 500,000 from both sides, which gives me 2,500,000 is equal to 33,388x And then we'll just divide by the 388x for the, no, not the x, but by the 33388. And that means that x is going to be equal to, since those cancel out, when we divide that, it comes to approximately 74.9. So we would say almost 50 years, almost 75 years later. So say circulation will reach, or will reach 3 million in about 75 years. Almost 75 years later. About covers the approximation for it. Something that would make sense for that. So this example shows, with weird big numbers, still finding a method here like this to generalize it, where it's like for x or for t number of years. So for 1 year, 2 years, 3 years, and then t years, because we see what changes here. Okay, so we put a t there. And that gives us the equation, and that's actually a slope and the y-intercept in it. And then you can use that to graph it. Okay. So using a couple of points here, I could graph and make sure, see what it looks like. And that could be different if I use different numbers on the sides, but this still gives an idea for this one. Right. And that was, and then the circulation after 56 years, and then how long it would take. Now, I got to watch something that says in what year. So in a way, I didn't answer. I just said in about 75 years. So what we've got to do is take the 44 and add 75. So I am going to now erase the yellow and say we can't stop there. What we have to do is do 75, or approximately 75, plus 1944. 1944 plus 75. So that's what, 9. So this should have reached should have reached 3 million at about the year 2019. Okay. In 2019. Based in space, I think that'll work pretty well. Interesting. And because that says in what year, not how many years later. So I need to answer it based on that. Whew, lot in this one. Okay, but this works when you recognize, here's the first thing to do, make the equation. The second thing, you can graph it, just thinking carefully about what numbers you put for time and circulation there. And then third, for 56 years. And then fourth, to get to that total amount, you can then solve for x for the number of years to add to get what year it's in. These are two applications of graph to equation and then using the equation. All right, thank you for watching and listening, and hopefully this is helpful for these kinds of graphing application problems.